Welcome to Young Tuition. Let's continue our discussion on Veritasia's big misconception about electricity. Some people may ask why I pick up this title, Veritasia's big misconception on electricity, as this video series. Well, when I first watched his video, I realized that not only there are many misconceptions about electricity, he has been trying to promote and propagate based on his fame. But also, there are some hidden agendas, in my opinion, that is a driving force behind this phenomena over the internet. So that is a little bit of the introduction of my video series. Today, I'm going to introduce another new hypothesis I recently made on electricity. And I can tell you that I spent more time to prepare this video than other videos I published. I can say even before the last Christmas. And I began considering relevant research. And it is not until recently that I came up with some new ideas. Let's go. So the title today is Electron Density Distribution in DC Circuit. The subtitle is The Devil is in His Details. Indeed, if you just look at relevant issues behind some seemingly simple ideas, you will find that the outcome, the conclusion you might draw would be very much dependent on the details at scratch, at the ab initio level. So let's consider this example to see how can I came up with this new hypothesis. Well, electron density distribution is nothing new, and formally that traditionally people would argue that charge distribution on surface, including the surface, so-called interface between the conductor and resistors, might play a very essential role in determining the equilibrium state of the electricity, namely the constant current and the distinctive voltage drops across different resistors. My hypothesis is rather simple. I believe that the density of electron provides very important role, which is consistent, which is similar to the traditional idea that the charge distribution plays certain role. But fundamentally, my hypothesis here is different from the one you might have heard before. Some people raise this issue on my channels repeatedly as if this is something settled down, namely the surface distribution of charge in the circuit involve, among other things, resistor. But I don't think so. Now here is my description. So in this origin rectangle, which represents part of conductor wire, which is a simplified conductor wire. From here you can see these red circles represent the lattice atom. So you can imagine that this is not real. This is ideal conductor wire. Only involves a straight line on which you can find the lattice atom. These green dots represent electron. Okay, so some electrons are bound, tightly bound by the lattice atom. Others have more or less freedom. Others, the rest of electron can be considered as a free electron. So that is my model in this context. Now, I use two axes to represent this variable of distribution. So one is x, which is longitudinal. That is in the direction of the parallel to the conductor wire. Another, the perpendicular one, the y-axis, which represents the transverse direction. So if we just put the origin of this coordinate here, 0, the origin here at the middle part, then you can see this R will represent the radius of this wire if we consider this cross-section is a circle. Now, these three curves here will represent the transverse distribution of electron density. So the middle one is the yellow one is almost uniform, which means that that is the electron density distribution in the absence of externally applied voltage. When the external voltage is applied on the two ends, then we might get some departures from this normal distribution. The purple one represent the electron deficit. In other words, some electron might move away to certain parts or along the one direction in the DC circuit. The green one represent electron density surplus. In other words, some part of the conductor wire or resistors might contain more electron than that in the absence of applied voltage. Okay, so this is so this diagram is the same. So we just rotate this the y distribution as a horizontal direction. So that is three distribution of the electron density. I just repeat, the yellow one is normal distribution, almost uniform, and the green one represent the electron surplus above the normal value, and the purple one represent electron defect. Obviously, if that is the case, then we can argue that if you go to the longitudinal direction, the x-axis, we will also encounter three scenarios. The middle one is normal. So the vertical axis represents the longitudinal electron density. Due to that, the transverse electron density distribution we just mentioned. So you can see that if you go along that x-axis along the conductor wire, and you might encounter different scenario that the electron density might be different from the normal distribution. From the normal distribution, not the Gaussian distribution, from the original distribution. Why? This applies this idea to the DC circuit. First, let's consider a capacitors. If you connect a capacitor with a battery, then immediately after a very short period of time, you will obtain this static distribution in which one side of capacitor will be full of a positive charge. another side will be full of the negative charge. Because in conductor, the only movable particles are electrons. So therefore, you can also equally argue that the negative side, negative charge is due to the electron surplus, while the positive side will be due to the electron deficit. So if you follow this diagram, then we can obtain this electron density distribution across a capacitor. Notice that the electron density is 0 between the two metal plate, right? And the detail of this curvature here is very much dependent on, the specific condition you encounter. So I wouldn't go. At this stage, I just use this sketch to illustrate my idea. Okay. So this would be the case for the capacitor. So what would happen to the resistor? Okay. Traditionally, people will prefer to still use this capacitor model, arguing that once you switch on the power, the DC power, and then the interface between the conductor and the resistor will be accumulate either positive or negative charges, so that to create the electrical field from the positive to negative, in order to explain that why electron can move from the negative to the positive side. All right, that is a traditional description. And actually that is why I have waiting for a few weeks before I publish this video, because I have been, my first response to this traditional description is that capacitor is fundamentally different from resistor. So here is what I have obtained. If you just consider a resistor, a single resistor in the battery, and this, although the material is not a perfect conductor, still in the resistors, we still can find electron move from negative to positive. So this is fundamentally different from the capacitor. That is why I reject the claim that the so-called interface between the resistor and the conductor can accumulate certain amount of the can form certain charge distribution similar to a capacitor. I disagree here. So what is my explanation here? Well, before we go further, another thing we have to mention that is that in the case of the capacitor, the electron density on both sides are different. And on the positive side, we got electron deficits, not just on the plate, but also along the conductor. Okay. The reason that the density cannot go to 0, because if we return to that structure, it is impossible, because after all, the positive lattice atom nuclei could still hold certain percentage of electron. So that is why the so-called the positive side is just due to the deficits of electron. So therefore, you can see that the potential difference between the positive and negative side is clear. That it would be the difference between this the red color and the purple color. That will be the difference, potential difference across the capacitor. In the case of the resistor, this is my hypothesis. I argue that the electron density would not form the distinct two delta function-like distribution at both interface. Instead, the density will continually change from deficit on the right-hand side, on the left-hand side, and eventually became surplus to on the negative side. In this way, we can still explain that certain voltage is created because the density, the more negative charge, the voltage is the potential, electric potential would be proportional to the amount of the charge. The more negative charge, the lower the voltage, the lower the electrical potential. Okay, the higher electron density, the lower the electrical voltage, the lower electron density, and the higher the electrical potential, which is consistent with our conventional description of the simple DC circuit with one resistor. Okay, but this is represented by this idea. So in both capacitor and resistor, we can got this voltage drop across this capacitor and the resistor. Now, the difference between the capacitor and resistor is that for the capacitor, there is no current. There is no current between the two plates. So therefore, the drift speed is always 0 on both sides. However, for the resistor, the drift speed is always there, is not 0 on both sides, including the inside resistor. So that is what my hypothesis says, that the drift speed of electron varies when you cross a resistor. If you combine these two diagrams, you will see that the lower the electron density, the higher the drift speed would be, and vice versa. So from these two diagrams, you can see that my argument is that the electron density distribution should more or less close to this this figure instead of the distribution we can find in the case of the capacitor. All right. So in addition, it must be make it clear that this change of the drift speed is natural. Okay, let's answer this final question first. How can drift speed change due to the electron density? Well, just use common sense. When the density decreases, the more electron can move relatively free, and vice versa. That is simple reason. You don't have to consider, additional electric field to look after this variation. After all, by definition, the current, electrical current, can be written as the first derivative of the charge with respect to the time. So if you just rewrite the charge as the delta E times delta L, then we can obtain this simple formula, namely the current, the electrical current equal to the product of the electron density and the drift speed. So V here is the drift speed. Therefore, as a result, because of this complementary dependence, reciprocal dependence rather, you can see that the current in the DC circuit can be maintained as a constant. Do you know what I mean? So in this 3D diagram, this is a 3D diagram, you can see that this curvature here represents the constant electrical current for each pair of different electron density and drift speed. Okay, the product of these two numbers will give you the current. So this is my new hypothesis about the electron density distribution in the DC circuit. In this case, the source is simple as a battery, just simple battery. Why did I pick up these topics this time? Because I haven't discussed the scenario of the circular loop we discussed before in the presence of induced electrical voltage or electrical field. I will discuss this issue in my next video. I hope you will enjoy watch this the video, and please like and subscribe, and let's achieve our goal to reach 1,000 subscribers. And by then, I will publish more fundamental and detailed discussion about the big issues in relation to Veritasia's big misconception about electricity, as well as in modern physics. Thank you and goodbye.